Up to this point, this class has focused mostly on upper bounds for problems. That is, we have a problem and we provide an algorithm that solves that problem. One might naturally ask whether these algorithms are the best we can do, or if maybe by being a more clever algorithm designer, we could have actually done better. Well, today we're going to see some natural barriers for algorithms, in the sense we're going to prove some information theoretic lower bounds. I mean, lower bounds in the sense that no matter what you do, even if you're a more clever algorithm designer, you're still not going to be able to get better accuracy or smaller sample complexity or need smaller data set sizes in order to solve these problems. So the approaches I'm going to talk about today are focused on pure differential privacy. We're not going to talk about techniques for approximate differential privacy, which are generally more complicated in order to get good lower bounds in those settings. And we're going to focus today mostly on two classes of queries, which we've seen before. These types of these approaches for lower bounds hold more generally, but just for simplicity and for illustration, we'll talk about two main settings. So the first setting we're going to consider, or one setting we're going to consider rather, is one-way marginals. And these should be, I guess we've talked about this before, I think, but maybe not with this terminology. So in this case, our data domain is going to be, we're working on over the Boolean hypercube in d dimensions. That is 0, 1 to the d is where our data lies. And we wish to answer the set of d queries of the following form. So we're going to essentially ask, how many coordinates are how many data points have a 1 in each coordinate, roughly, or what fraction of them. So more precisely, the jth coordinate of this form is going to be summation, the average 1 over n, I equals 1 to n, xi j, where this means that it's the jth coordinate of point I. So yeah, you can see this as like one example of where this comes up is, imagine you want to ask a set of people their answers to a set of d questions, and each one they give you a yes or no answer, and this essentially says you want to find out what fraction of people said yes to each of those questions simultaneously. That's the first setting that we're going to consider. The other one is perhaps more familiar, which is histograms. And in particular, we have here now a data domain, which is, let's say the numbers 1 through k. We could really let it be any sort of discrete domain, but we're just going to let it be the numbers 1 through k just for simplicity. And we want to answer the k queries of the following sort. So the jth query will be like of the following. It'll be, how many of the data points are equal to j. So let's just write it like this. And, you have the indicator function here, which gives you a 1 if xi is equal to j, and it'll be 0 otherwise. And for both families of queries, we're going to measure how good our accuracy is in terms of L infinity error. That is, we want to answer these queries such that every one of them simultaneously is correct with low error. That's what we mean by when we say L infinity here. We're going to say we answer all of them correctly to whatever accuracy we say. Okay, so what do we know about these problems? Like, what type of bounds do we have? Well, for both of these, we've seen both upper bounds and lower bounds. We've only seen upper bounds, but we've seen upper bounds in both pure and approximate DP. So first of all, what have we seen for, say, the one-way marginal setting? Well, remember we talked a lot about, just answering linear queries and counting queries. So in particular, for this type of thing, it's very easy to just apply the Laplace mechanism. The Laplace mechanism is the most basic type of algorithm for this. And under pure DP, it'll give you an algorithm which takes, I'll write this one a little bit more out. So under pure DP, that is epsilon pure DP. So if we're given, say, n greater than, d over alpha epsilon, and I guess we need another log d here for a union bound style argument, then we have error less than or equal to alpha for all one-way marginal queries, and say with probability greater than or equal to 1/2. You can really get this much higher than 1/2, but we're just going to use 1/2 for illustration. So this says that you can answer all one-way marginal queries, and the sample complexity, or I'm going to use a sample complexity as a term for how much data we need. The sample complexity is going to be d over alpha epsilon. Get error or accuracy alpha. So that's for pure DP. However, for approx DP, we saw something similar, except with a better, a smaller n by a factor of square root d roughly. In particular, for approx DP, you could just use the Laplace mechanism again, but this time we use advanced composition, and that gives us the bound that we need n to be greater than or equal to square root d log 1 over delta all over alpha epsilon. So that is the bounds for one-way marginals. You can see that there's quite a big gap between these two. In particular, there's a square root d factor difference between them. So yeah, the question is whether this is an intrinsic gap, whether the pure DP problem is intrinsically harder than approx DP, or whether maybe by being a more clever algorithm designer, we could actually get this d log d all the way down to this square root d log 1 over delta that we have here. And as we'll see later on in this lecture, the answer is in fact no. Roughly d over alpha epsilon is the best you can get. All right, so that's for one-way marginals. How about histograms? Well, we have a similar type of understanding here. So if we want a pure DP algorithm, we can just use the Laplace histogram algorithm that we talked about in lecture 4. And that gives us the bound. I'm not going to write the whole thing out again, but the number of samples we need, the amount of data we need rather, is n to be greater than or equal to something which is omega of log k divided by alpha epsilon. And this will allow us to answer all histogram queries in L infinity distance. Essentially give you good counts of what fraction of items fall into each bin. And in approx DP, in just the last lecture, we saw that there is a stability-based histogram, and that can actually avoid the dependence on k, the domain size, altogether. And this requires n to be greater than or equal to log 1 over delta over alpha epsilon. And what we're going to see today is so let me just highlight the two lower bounds that we're going to see today. Essentially, this is an upper bound that I wrote here, but we'll see also that we have a matching lower bound for this, and we have a matching lower bound for this right here. Essentially, if you are unable to if you have fewer than this many samples roughly, we're going to cross off this log d here in our lower bound. We don't quite match this upper bound, but the idea is if you have fewer than log k or d many samples here, then in fact you won't be able to solve these problems with any sort of non-negligible probability. So those are the type of results we're going to see today. The style of argument that we're going to see is going to be a packing approach. So these are often called what's known as packing lower bounds. And the term packing comes from the idea of trying to construct many different data sets, which each give different answers from each other on the set of queries. So just to give you sort of metaphor, which may or may not click with you, but imagine you consider packing many rigid balls into a box. So you have a box and you try to put as many balls as you can into that. And we have the guarantee that every ball here will be far from each other because, the centers of two balls will be far from each other just because of the fact that they're rigid balls. So that's what I mean by every two things will be far from each other. And in some sense, the more data sets you can pack into the space, then we'll get stronger and stronger lower bounds. So the goal is really to try to find the most effective way to pack data sets in so that they're all sort of pairwise far from each other. Clearly, you can't put too many data sets into the space, because if you have a lot of data sets, then eventually you're going to run out of volume, and then you won't be able to fit any more databases in without making two, say, close to each other. This was a little bit abstract, but we're going to make it a little bit more concrete in a second. So the argument is kind of rather elegant at its core, though it can get more technical for more advanced cases, but nothing we see today will be super, super complicated. But it might be a bit unintuitive at first, because lower bounds are typically a different style of thinking than upper bounds. So yeah, try to pay attention and see if you can really internalize the type of argument we're doing here. But essentially, at its core, packing lower bounds follow the same type of argument. So what we're trying to lower bound, the way the argument generally works is of the following form. You're supposing that there's an algorithm M, which is both private as well as accurate. And we want to say that, okay, since it's supposed to be accurate, this means that we're going to have to give different answers for every database, because there's some databases which would naturally have one answer on them, and other databases which would naturally have another answer on them if the true query gives something different. So for a bunch of different databases, you'll have to give different answers. On the other hand, privacy somehow goes in the opposite direction. It tells you that suppose you have two different databases, which are maybe you change just a few points to get from one to the other, then those will have actually similar probability distributions over the sort of output space. So just to kind of hammer it home, the accuracy guarantee says that the answers on different databases are different from each other, whereas in some sense, privacy says that the answers on different databases are going to be similar to each other. So these work against each other, and when we combine these two constraints, then that implies that they can't both hold at the same time unless we have sufficiently much data, unless we have some sort of lower bound on n. And that's roughly how the argument works. Again, this is a little bit abstract, but let's do this with a very simple example, just so you get the idea. Like we're not going to prove a theorem here or anything. Okay, I guess you could summarize our findings in a theorem, but we're going to do this very sort of casually, just to sort of see how an argument like this works. So let's suppose we're trying to output the mode of a data set over a domain. We have a histogram with k-bins. And what we want is an algorithm. We want to prove a lower bound on, an algorithm M, which has the following two properties. One, that it's epsilon dp. And the other characteristic that we want to have is that naturally we're trying to find the mode. So what we want it to do is output the mode of whatever input data set is given, x, with probability, say, greater than or equal to 1/2. We could put whatever constant we want here, but just for simplicity, let's say it gives the right answer with probability at least 1/2, right? If it doesn't even give probability 1/2 of getting the right answer, that's a pretty bad algorithm. All right, so what we're going to do is we're going to consider, let's suppose there's a set of k different data sets. We have, D1 all the way through dk. These are different data sets, and we define the jth data set as follows. So dj is going to equal, it's going to just essentially equal the jth data point n times. So each of these databases is going to be completely just one element. You just repeat it a whole bunch of times. So let's just draw out what these look like. So here is, let's say these are the different bins. I'll just put them as points. So there's 1, there's 2, 3, all the way up to k. And so what the first database will look like is just having, you know, D1 will just be something like this. So right here, this is D1. It'll have this being 1 and everything else being 0. Whereas you can define all the other databases rather similarly. For example, this right here will be dk. Like I said, this is 1. And yeah, this is 0. So that's the rough idea. We're going to have, these are the different data sets we want. And so let's look at what the algorithm should give on each of these. For example, on D1, clearly the mode is going to be 1, right? It's the only one which has any points at all, so therefore it's clearly going to be the mode. And similarly, dk should have k being the mode. So let's fix some specific j. And let's consider the distribution of m on dj. Distribution of m on dj. So what can we say about the distribution of m on dj? Well, m on dj has the following property. Since the only valid outputs here of what could be the mode are 1, 2, 3, all the way through k, that means it's a distribution over, you know, items 1 through k. In particular, since it's a distribution on 1 through k, therefore there must exist some symbol L. So there exists some symbol L which is in k, such that the probability that m on dj is equal to L is less than or equal to 1 over k. So just remember back, this is the pigeonhole principle, essentially saying that, you know, let's say there was no such a symbol where the mass was less than or equal to 1 over k, then just summing it over all of the things, it would sum to something which is greater than 1. So there exists at least one symbol L such that the distribution of m on dj is less than or equal to 1 over k. So that's what we have in terms of the probability distribution of this. However, what else do we know? Well, the accuracy guarantee tells us that is, you know, this accuracy guarantee right here saying that it outputs the correct mode with probability greater than 1/2. Well, that tells us something about a specific the algorithm behavior on a specific data set. It tells us that probability that m on dl, the probability that this is equal to L, is greater than or equal to 1/2. So this is the accuracy guarantee. Let me just point this out. Right. Now, we almost have everything that we need. The last observation that we need is the fact that, 1, the algorithm is differentially private, and 2, the fact that we can change the dataset from DL to DJ by changing n points. This is a trivial observation, but essentially just saying that if you change one data point at a time, you can convert any dataset to any other dataset. And that'll be useful for, recall, group privacy. So we'll get to that, but what do I mean by that? How will we use this? So first of all, let's just write this inequality. So 1/2 times probability, let me say this, 1/2 is rather a lower bound on the probability that m on d of L is equal to L. That's, you know, just the accuracy guarantee. And next we can say here is the group privacy guarantee. So what we're going to try to do is relate that probability to this probability. And so we're saying that this is less than this times the factor of e to the epsilon times n. And the reason for this is, again, like I said, group privacy. You imagine you can change dl to dj just by changing n data points. And if you recall what group privacy says, it says that it'll be a factor of e to the epsilon n rather than e to the epsilon. And now the final step is just using this bound we said here, just based on the fact that there are many different possible outcomes. And this can be upper bounded by e to the epsilon n divided by k. And that's essentially all that we need. Now, all we do is put these to the left-hand side and the right-hand side of this together, and taking the log of both sides, we can get that n is greater than or equal to, let's say just omega of log k. Let me do this slowly just because this is the first time you might have seen this. So let me do this nice and slow. We have the inequality at the end, e to the epsilon n is greater than or equal to k over 2. So taking the log of both sides, that gives that epsilon n is greater than or equal to log of k over 2. And this gives that n is greater than or equal to log of k over 2 divided by epsilon, which is equal to omega of log k over epsilon. So what did we see here? What exactly did we show? We showed that we imagined we started with an algorithm. We wanted some algorithm which is both private and outputs the mode of this whatever data set you feed in with probability 1/2. Well, we gave it just a small set of databases. It has to be at least correct on each of these databases. So we showed that if it's correct on all of these databases, and it's also private, then in fact, it must be the case that n is greater than or equal to log k over epsilon. Otherwise, either the accuracy or the privacy would have failed at some point. And that's just the style of the argument. This was sort of very intuitive, but we're just going to kind of formalize this type of argument. And I don't know if we even have to formalize it more, to be honest. Like if you got this, I think this is as formal as it really needs to be, but we're gonna maybe set it up with appropriate theorems just because that's what we do in this class. Okay, so let's try to, generalize, or let's try to write down some of the core tools that we used in this proof in order to maybe use them for other proofs. And the kind of key property was this is this key packing theorem, which I'm going to call it. And the idea is the following. Suppose we have a set of m data sets, each of which are at Hamming distance at most t from some fixed data set d. So they're kind of all close to some data set d. So you might see already where this is going to come in. Remember, we use group privacy to change from one data set to the other, but we just use a very naive bound of things being at distance less than n. Here we're going to say that they're at distance, Hamming distance at most t from each other. Remember, that's the number of points you need to change to get from one to the other. And we're going to say those are the data sets, and let's also at the same time let y1 through ym be a set of m disjoint subsets of the space y. So that's sort of like the output set of the algorithm. So the key thing, the important thing is that they are disjoint. That is, they don't overlap. And the reason that's important is kind of because of the fact, like similar to the idea we used here, these are different sets of the output. And so we have a distribution over the probability that falls into each of them. And you don't want to have to count for probabilities in the overlaps. But yeah, so it's kind of important that these are disjoint subsets of the output space. And so these are databases, subsets of the output. And we say that if there's an epsilon differentially private algorithm, which has this sort of accuracy guarantee, and that says that the probability that the algorithm, when run on dataset L, has an output which is in set L, and that probability is large, say p, you can think of it as being a constant, say like 1/2 or something. Then for every one of these data sets, if we have this for every one of the data sets, that is, it's accurate on every one of these data sets, then we have the following rather kind of weird bound. It might not be clear why this is useful or anything, but yeah, we'll see. We have sort of a relationship between the value of p, t, epsilon, and m. So let me just sort of maybe there's too many parameters here. Let's sort of look at a simple case. So suppose that we have p equals 1/2 and t equals n, just for simplicity. Note that these are exactly the same parameters we had here, that t was equal to n and p was equal to 1/2. In that case, then we would have a theorem which is of the form, the guarantee at the bottom would be something like, what is it? We would have that m is less than or equal to 2 times e to the n epsilon. And in fact, if you take the log of both sides, you can see this pretty similar, almost exactly what we had before. But this is just a slightly different, slightly more general phrasing of it for convenience, and we'll see, how it's useful later, especially this t equals n. Changing that to other parameters, setting t to be smaller values, is sometimes useful in terms of getting better lower bounds. Okay, so this is to give you a flavor in why this type of thing is useful, because it'll let you show something very similar to before, and that'll give you sort of a lower bound on n. But let's see how to prove this. And it's a very simple proof, actually. It's maybe like 2 or 3 lines. So let's see. What are the steps? The first step is just saying, okay, I'm just going to rewrite the accuracy guarantee. We have that probability that m on dl, the probability that's in its set, is greater than or equal to p. Now we're going to use group privacy, and remember, we're going to use the fact that this fixed data set is close to every data set simultaneously, but in particular is close to dl. So what does group privacy say? Group privacy says the following. It says that probability that m on d of l, probability that this is in the set, this is going to be less than or equal to e to the t times epsilon, probability that m on d is in y sub l. So this is just literally the definition of differential privacy, where we invoked group privacy. And this is because, yeah, like I said, there are d and dl are less than distance t times epsilon from each other. So putting that together with the previous thing, that tells us the following. It tells us that probability that m on d is in y sub l, this is greater than or equal to e times e to the minus t epsilon. That's just combining this and rearranging. Okay, now since these YLs, now here's where we're going to use the disjointness, the fact that these are disjoint subsets of the space. Well, we have the following bound on probability that m of d falls into sort of the union of these. So what do we know about this? Well, the probability that it falls into the union of these, like these are, this is possible different outcomes. This is going to be at most 1, just because it's, you can't have the probability be greater than 1. So the fact that they're disjoint comes in here is we just separate this union into a sum. And that gives us that summation of probability that md is in y sub l, where the summation is again over L in M. Now, the last thing we use here is just this, what we have had above. So that this is going to be greater than or equal to, now we just replace the summation by m, because that's the number of terms in the summation, m times p times e to the minus t over t epsilon. And so yeah, that's the whole proof. Like if you take a look at here, take a look at the left-hand side, and you take a look at the right-hand side, if you just divide both sides by m, then you have exactly this relationship that we have here. That's it. So this is the key packing theorem, as I'm going to call it. So okay, that's the packing theorem. Now let's see how we use this theorem. And we're going to use it to see two different lower bounds, one for one-way marginals and one for histograms. So first we're going to do one-way marginals, and we're going to keep it a little bit simple at first. We're going to fix in particular that our accuracy alpha is just accuracy 1/2. We don't want to be sort of grossly or blatantly wrong on any query. So here's the theorem that we're going to prove. We want to show that any private algorithm, M, which takes a data set of, sorry, I think this is, yeah, this should be 0, 1 to the d times n, not just this. And the idea is that the domain, each data point is going to be in 0, 1 to the d, and there's going to be n different data points, or potentially the same data point. But yeah, there's going to be n data points, and then we're going to map that to just a vector which tells you what fraction of each coordinate is 1. So any private algorithm M which simultaneously answers all of these marginals to accuracy, say, rather this should be maybe not to accuracy, to error, maybe to error less than 1/2 with probability at least 1/2, requires that n is going to be at least d over epsilon. So let's just try to apply this key packing theorem we had up here. Let me sort of borrow this, and we'll take this along with us because it might be helpful to refer to. Can I shrink this? Yeah, I'll keep it a little bit small here, but hopefully you can still just read it or maybe see some of the key notation here. Oh, it just looks worse. Okay, so hopefully that's good enough. Okay, so we have to construct a set of databases which have disjoint subsets of the output space. So what we're going to do is choose a bunch of databases which have very different answers on these one-way marginal queries. So what are the ones which are sort of the most different that you can imagine? Well, we're kind of going to choose some very simple and silly looking databases. So we're going to choose the following set of M equals 2 to the D different databases. And we're going to do the following. So for all W in 0, 1 to the D, we're going to have that we define database D sub W is equal to n copies of W. So this is very simple. Yeah, every database is just going to consist of a bunch of copies of the same data point. Seems kind of weird, but on the other hand, you know, it's very simple in terms of knowing what the answer should be. For example, if your string is the all 0 string, then the correct answer to that is going to be just the 0 string. Yeah, in particular, ideally we would like that the algorithm M on DW would just be equal to W, but that would be perfectly accurate with error 0, but that wouldn't at all be private, right? So we're going to let the database be this, and we're going to define the set Y sub W to be the set in which M of DW should lie. So this is kind of the set of correct answers for DW, for M on DW. So we'll say it's okay if I'll write it in words first. We essentially want an L infinity ball of radius 1/2 around W. So that's what we want YW to be equal to. And sort of in math, it's defined as the following. So it's the subset, it's all x in 0, 1 to the d with the following property, that we have that x sub j, the sort of the jth coordinate of x minus w sub j is less than, strictly less than 1/2. And we have that property for all coordinates, all j and k. So this might seem a bit arcane. Let me see if I can make it a bit clearer. So let's just like draw a two-dimensional picture, you know, because I can only draw squares in 2 dimensions, maybe 3 dimensions if I really tried. But yeah, the idea is the following. So this is like 0, 0. And this is, you know, I don't know how to do it, 0, 1. And this is 1, 0. And this is 1, 1. And we're going to say that y of, let's say, 0, 0 is equal to this, this sort of subset of the square right here. And, you know, any point that's sort of in this little corner of the square is going to be an okay answer for if we're given in the data base consisting of n copies of just a 0, 0 string. You know, you don't want to step outside of that because that's the region where one of these other things should give their answer. Okay, and I claim that at this point, we're pretty much done in the sense that we want our algorithm to simultaneously answer all one-way marginal queries to accuracy or error less than 1/2. So what we want, really, translating this like theorem statement, is that we want that probability that m on d sub w is in y sub w with probability greater than or equal to 1/2. And so we can just use this theorem as is and, you know, plug in the appropriate values. We have that p is equal to 1/2. We have that, let's write some of these down, p equals 1/2. T, we're just going to use the trivial value of n, just because we can always switch between any two databases by changing all the points. And the last one is the fact that we have m equals 2 to the d databases. Yeah, because we defined 2 to the d different databases here. And just plugging in these values, what does that give us? That gives us that 2 to the minus d is greater than or equal to 1/2 e to the minus n epsilon. And just taking the log of both sides and rearranging, this will imply that n is omega of d over epsilon, which is exactly what we set out to prove. So you can see how easy this was to apply. Like it wasn't really hard at all. I think it's kind of surprising and kind of elegant, the fact that, you know, we went from nothing to a proof that this algorithm is that we can't improve upon some of these basic algorithms that we did in how many lines. Like we set up this theorem, which was like maybe 2 or 3 lines, and, you know, the construction was very simple to instantiate this lower bound and prove that we can't do better. So I think it's kind of beautiful how simple this was. The steps might have seemed unmotivated if you haven't seen lower bounds before. But once you get it, it's really quite nice, I think. So try to really internalize it, like I said. So let's reflect on what we just proved. This shows that if we want to estimate the one-way marginals of a data set under pure differential privacy, we really need n equals omega of d. On the other hand, we showed that in a previous lecture, we've showed that if you want to prox dp, then n equals O of square root d over epsilon, roughly, works under a prox dp. So this shows that there's an inherent gap between approximate dp and pure dp, in case you want to solve it under these two different constraints. So like I said, we're not going to show any. I'll claim also that this is pretty much tight as well. You can't do better than that. And this is shown via a more complicated technique known as fingerprinting, which I don't think we're going to get into in this course. It's more complicated, I'd say, than packing for sure. Okay, so this was a nice lower bound. We saw how easy it was to apply this theorem 1. All we needed to do was select the right packing of databases, and the results followed almost instantly. We're going to see how to apply this one more time for proving lower bounds for histograms, and then we'll call it a day. This time I'm going to do something that's a little bit trickier than this one. In particular, here we focused on accuracy or error less than 1/2, but the next lower bound that we're going to do will go up to, say, arbitrary accuracy, where we parameterize that like the error is less than alpha. So yeah, you can do more fine-grained answer than this and give accuracy or error alpha, but the argument is a little bit more, just a little bit more sophisticated, not much. Yeah, I just wanted to keep it simple the first time. In fact, you could do the same change that I'm gonna do for the next part, also for this type of theorem, and also get, essentially it's possible to prove something with error less than or equal to alpha with d over alpha epsilon, but I just didn't do that just to keep it simple for now. All right, but here's the theorem that we will prove for histograms, saying that any epsilon dp algorithm M, which takes in a data set over the domain 1 through k, and outputs a set of values, one for each of the domain elements, and this will sort of add up to be a distribution, will be normalized. So any algorithm M which estimates all histogram counts to accuracy, or I guess error again, less than alpha, with probability at least 1/2, requires that n is at least logarithmic in the domain size, and we have this 1 over alpha epsilon multiplying it this time, not just as 1 over epsilon. Okay, so let's see how to prove this. The proof is pretty similar to before. We're just going to construct a set of databases, and we're going to sort of work in, instead of we have x in k to the n, but we're going to find it more convenient to work in the histogram representation, or the normalized histogram representation. So h of x, which is in 0, 1 to the k, and this is just going to be the sort of normalized histogram representation. This is exactly what we said before, where h sub x and the jth coordinate of this will be equal to sum of 1 over n. Basically, the number of points in the data set which are equal to symbol or domain element j. Yeah, just normalizing it because it'll be more convenient. Because in fact, this is exactly the right answer that we would like to give. We would like that algorithm M on dataset X would return h sub j of X, or the set of h sub j's on X. It has to give it for each coordinate. So that's ideally what we would like, but of course that would not be private. So what we're going to do is, this is our sort of ideal, but what we're going to do is say that let y sub x, which is a subset of 0, 1 to the k, this is going to be sort of the space around h of x. So in particular, we're going to let this be y sub y of x is going to be the L infinity ball of radius alpha around h of x. So what I mean by that is essentially the y sub j on x will be the interval which is equal to h sub j on x plus or minus alpha. So this gives you an interval, and that'll be that'll be the set y of x. And why did we define this? Well, the accuracy guarantee, when we say it estimates all histogram counts to accuracy or error less than alpha, then what we really want is that the probability that m on x is in y of x is greater than or equal to 1/2. So this is the type of accuracy guarantee we want, and yeah, we're just going to have to choose how, again, to choose our data sets in order to create our packing and have things work out nicely. So let's see how to specify these data sets. Let me once again borrow this just because this theorem could be useful in case for your reference. I'll stick this up here. We know what histograms are. Okay, so what we're going to do is we are going to try to construct a set of databases, and we're going to do it in the following way. So we're going to define D1 through dk. So there's going to be k databases, m equals k databases. And we're going to construct them in the following way. So this might seem a bit funny at first, but the reason we're going to do it in this funny way is just because we want this alpha to show up. Like I said, it's a little bit more complicated than before, but not much. So the way it works is database DL is going to be equal to the following. It'll have t copies, t equals 2 times alpha n copies of L. And it'll have the rest be just the symbol 1. Sorry, not that. And this might seem a bit weird, but it kind of works out okay. Let's see what exactly these databases look like. So let me draw some of them for you. So let's draw the simplest one, which is a special case actually. Let's draw D1 first. So 1, 2, 3, all the way up to k. So the first database, that is D1, will look just something like this. It'll have all its data points on symbol 1, D1. On the other hand, everything else will look a little bit different. Let's draw it for sort of a generic DL. Like 1, 2, dot, 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 L, dot, dot, all the way up to k minus 1. So what this one will look like is it'll look a little bit different. So there's going to be somewhat less mass here. There is going to be, here we have 1 minus 2 alpha. And then on symbol L, we have mass 2 alpha. And that's what it's going to look like for each of these other databases, DL. And why did we do this? Why did we sort of put this amount of mass here? Well, let's see what exactly, let's see what y of remember we drew this L infinity ball around the true histograms for each of them. So let's see what these, the sort of allowed answers are going to be for each of these. Let's see what the y sets are for each of these data sets. So suppose we're given the data set D1, then the set of outputs that the algorithm M is allowed to give and still attain the right accuracy guarantee looks something like the following. So it's allowed to output any point that's within the following. Let me try drawing this, and so on, all the way up to here. So what does this mean? This just says that the first coordinate has to be within between 1 minus alpha and 1, and everything else has to be between 0 and alpha. If it's not within 0 to alpha, then it's incorrect, and similarly, if it gives you a value here, then that's incorrect. Okay, and whereas for here, in this one, note that it's capped at 1 because we say that the output has to be within 1. Within 0, 1 for each coordinate. Now for this one, for say arbitrary data set L, we have the following. We have in fact that for sorry, we're going to have sort of 3 different cases for all of these. So for anything that is not 1 or L, we have that the value is going to be between 0 and alpha. For the symbol L, we have that the value has to be between alpha and 3 alpha. And for the last one, we can see that this is going to have to be between 1 minus 3 alpha and 1 minus alpha. So you can see actually, if you take a look, there is no single histogram which lands in both of these at the same time. Not necessarily a histogram, but no single vector that of potential answers which would be correct for both this and this at the same time. We've kind of chosen it uniquely so that none of the sort of right answers overlap. Yeah, in particular, you can't choose a value which is simultaneously in all of the red regions for both this and this at the same time. So therefore, this is kind of what we wanted to show, that the sets are going to be disjoint. In particular, let me just sort of state that a little bit more. So this kind of argument that we've said here is that if we let YL equal to Y of DL, then this implies that by this sort of argument we saw here, that the YLs are disjoint. Okay, cool. So we're actually almost done now. What have we done? We've almost checked all the boxes of this theorem statement. Where did that come from? All right, we've checked almost all the boxes of this theorem statement. All we really wanted was to say that let there be a bunch of databases which are at Hamming distance less than or equal to t from each other. So we've done that. We have a bunch of disjoint subsets of the space Y, and we have a mechanism which is accurate on all of them. Then we have the following guarantee. So let's just see what type of guarantee we got. So what was M? M was equal to K. We had K different databases. So 1 over K. This is greater than or equal to, we set P to be 1/2 just because it doesn't really matter too much for our settings. And times E, let's say exp of minus, now this time, note that we did something a little bit different. We set T not equal to N. Now we had a much smaller value of T. This is kind of why we chose this very odd setting of T, but we set it to be equal to 2 times alpha N, and then times epsilon. So that's what we got here. Let's just rearrange this and see what we get if you multiply it through by both sides, and you get to K is less than or equal to 2 exp of 2 alpha N epsilon. Take the log of both sides, you get log of K over 2 is less than or equal to 2 alpha N epsilon. And rearranging, you get what we were really going for. N is greater than or equal to log K over 2 over 2 alpha epsilon, which is equal to omega of log K over alpha epsilon. And that's exactly the lower bound we were going for. This is very nice. We saw here now a slightly more complicated argument, not really that much more. We had to draw this picture, which was kind of fun, but it was really not too much trouble to end up with a lower bound for histograms, which is actually, which matches the upper bound which we showed before. Yeah, in particular, you know, we just said that the simple naive Laplace algorithm is going to get the same type of accuracy guarantee. And this shows that you can't do anything better than that if you're restricted to pure DP. Like I said, you know, if you use stability-based histograms that we discussed in the last lecture, you can replace this log K with log 1 over delta. But yeah, that requires going to a relaxation of pure differential privacy. And that's it for today. Yeah, this is a relatively short lecture, and I think it really illustrated how simple these packing lower bounds are, and they show how powerful they are in terms of trying to prove that algorithms are optimal.